All right, so the best way to go about this problem is to first recognize that all the pull down networks and all the pull up networks are going to be complements of each other. So for example, in the first part, you see A and B are in parallel with each other. A and B are in A and B are in parallel with each other. Over here, A and B are in series with each other. Then that particular combination is in series with C. That particular combination is in parallel with C. And then all of that is in parallel with A and B that are in series. All of that is in series with A and B that are in parallel. So you see everything is complementary in nature. You see that? So, once you recognize that, what this means is I can just use the pull down network to solve this problem, or I can just use the pull up network to solve this problem. So because they are in pairs, they are complementary of each other. So to get X, what I can do is I can just focus on the pull down network. I could have also used the pull up network that is circled in red, but I will show you how they relate to each other in just a minute. Now my goal is going to be to write an expression, a logic expression for X in terms of A, B, and C. So that way I can quickly fill up the truth table without having to go through each and every combination. I can just write logic expressions and then plug in the values 0, 0, 0 and so on. That will be much faster and easier. So so let's go down to this and look at how do I write a logic expression for X by looking at the pull down network, right? So I'm looking at this guy right here. So what do I have? I have two NMOS transistors in parallel first, right? So I'm looking at A and B that are in parallel with each other. So for that, I would say X equals A and B are in parallel. So I would say A or B, right? Because things that are in parallel, we say A or B, right? And then things that are in series, we use the AND operation. So I've got A or B for that. And then that is in series with C. So I would AND it with C. Second. And then all of that is in, so here, let me show you this. Yeah, that. And then all of that is in parallel with A and B that are in series, right? So that is for that. But there is one more thing that is missing here, which is this is a pull down network. So I am writing an expression to indicate how it goes to 0. It's complemented. You got it. So what I'm going to do is highlight this a little bit, bring it down, and then I'm simply going to complement the entire thing. So that would be X. And then you can go apply the same logic. We also know that this guy here is a NOT gate, right? That's a CMOS NOT gate. So literally what you're saying is Y is X complement. And you know the equation for X, so X double complement. So you just get all of this for Y without the bar over the entire thing. And then that will quickly help you to fill out this particular column, the last column. All you have to do is fill in arbitrary values 0, 0, 0 all the way to 1, 1, 1, and then evaluate that logic expression for those inputs. Now the same thing you would apply to get an expression for, let's highlight this point and call it maybe Z, right? So you can apply the same logic and use the pull down network over here, obtain an expression for Z, and then W is going to be the complement of Z because that is another NOT gate. And that would give you the last entry in this for W. And that's the problem. So I wouldn't want you to use individual like combinations. Okay, let me put 000 and then go through the entire thing. Let me put 001, go through the entire thing. That is going to give you the correct result, but that's not a very elegant solution. That's a brute force method to find out things. What you really want to use is the method that I just described, using the logic expressions to develop the truth table, which is also going to be helpful for you to go back. So suppose I give you the logic expression, you can use that to draw the logic network. All you would have to do is recognize where are things in series, where are things in parallel, and when do I need to complement and when not to complement. Now, I also said that you could do this using the pull up network, right? So let me just show you how to do this using the pull up network. What you would be writing here for pull up network is X, for the same X, you would say A and B first are in parallel. So you would say A complement or B complement. That is in series, right? So that is for this. And then that is in series with a parallel combination of A complement and B complement or C complement. That's it. So using the pull up network, you would get that. Now my claim is that these two expressions are the same. Which this guy and this guy, these are exactly the same expression. And it is the case. Using De Morgan's law, you can actually prove that they both are the same. And we'll look at De Morgan's law today, but those are exactly the same expression. All right, so let me stop the recording here.